So in this video, we'll be talking about mechanism atlases and how to use them for synthesis. We'll first of all look at doing a path synthesis example and then move on to doing dwell synthesis, where dwelling is basically having a mechanism pause at some point during its motion and then move off of some location. So we often use this for holding an object in a nest or perhaps doing a clamping operation for a moment in time. We'll talk about how to do that. So first of all, let's talk about these atlases and specifically what they're going to be showing. What they're showing is a coupler point or a coupler curve in space. And just talking about a coupler, if I have this generic 4-bar down the slide here, you'll notice that I have all of these little holes in this coupler. Well, imagine that I take a pen and I stick it through one of these holes and then run the mechanism through its range of motion. Well, I would get a different path based on where I stuck my pen through this coupler. And these are what we refer to as coupler curves, and not only for a given mechanism do I have different coupler curves, but then I can adjust the length of the individual links and I get hundreds and thousands and lots of different ways to generate complex couplers or coupler curves. Now, the coupler curve of just a 4-bar mechanism like this is what we call a 6th degree, which means that with a certain configuration of it, I could have a straight line that would be intersected 6 times by the coupler curve. And the coupler curve has up to 3 loops. So this is a fairly complex curve, and if you were going to talk to one of the mathematicians in Lind Hall, this is called a tricircular sextic. So a fairly complex curve that you're trying to predict how is this going to behave based on the geometry. 4 bars are fairly simple. What if I jump up to a 6-bar? Now we jump up to an 18th degree curve. So mathematically quite complex, and if I go up to an 8-bar mechanism, now I have a 54th degree curve. So you can see why these synthesis tools that we have in the class are very powerful because they're allowing us to generate these high degree polynomial curves that are our coupler curves. All right, so what does a coupler curve look like and what are some common shapes that I can have? Here are some possible shapes. Anything from the upper left where I get sort of an ellipse. There are sometimes when you can get actually pure circles. We can get things that look like kidney beans or bananas or starting to pinch those down into crescents. We can get some coupler curves as well that will have a double straight edge, and these are actually very useful for dwell mechanisms. We can have some that have an approximate constant radius arc to them, and those we also use for dwell mechanisms. A few unique features that we will see on coupler curves, and we'll talk about where these are later on, is a cusp point. And this is a point where the coupler point's coming in here and then actually does pure rotation off that cusp point and moves off. So at this location, we actually have 0 velocity for 1 instant in time. And you can see we could have 2 cusp points like this one. If we move beyond the cusp, we can get to a Crew node where we actually have the coupler cross itself. And when we were talking about that these 4-bar coupler curves can have up to 3 loops, well, here you can see this. We're actually approaching 3 loops right here where I've got 2 Crew nodes right here as well as a cusp point. So I'm approaching a 3rd loop. If I move just a little bit farther off this location on my coupler, I would get a 3rd loop here. So that's what we mean by this 3-loop 6th degree curve. So very interesting shapes that we can create, and they've actually started putting these together in a variety of atlases. Now before we get there, let me talk about a couple of other very interesting curves that are quite useful because they are symmetric. So these are a set of coupler curves that based on a special set of link lengths are all symmetric. So you'll notice that the entire coupler curve has a line of symmetry right down the middle of it. Again, this coupler curve up here has a line of symmetry, intersects with the ground pivot. Again, this one over here has a line of symmetry, intersects with the ground pivot. And I'll talk about how to interpret these drawings in just a moment, but this whole set of coupler curves very unique in that they are symmetric, and that can be very useful based on what the objectives are of our mechanism. All right, so back to the atlas. Now, back in 1951, before we had really the computational capabilities that we have today to do the analytical synthesis, a lot of synthesis was done graphically and through atlas methods. So coming out of MIT, Rones and Nelson and really their grad students sketched a lot of coupler curves. There are 700 pages to this atlas. I wish I had a hardbound copy of it here. It's an oversized book, 700 pages, and on each page there are 10 coupler curves sketched. So there's a total of 7,000 coupler curves through these 700 pages. All of these are Grashof crank rockers, so we always have a unit input length and it's making continuous revolution or cranking. And you'll notice that this happens to be a page out of the coupler curve book. So this point right here that has 3 circles around it, that is the ground pivot, and this happens to be for the input link. This is then the input link right here, and this is my moving pivot. And then I have the coupler right here. This is the other moving pivot, 2 circles around it, and then 3 circles around the other ground pivots. So this is the ground pivot of the rocker link, and this is the ground link between them. And you notice the starting location is always with the input link collinear with the ground link. And then to get the different coupler curves, I take this coupler right here and I extend it out to any one of these other points that are shown here. So I could bring it out to this point right here and have that be my triangular coupler, and then I would follow this coupler curve right here. And so you can see that's one of the 10 that are shown on this page. And then we get this little diagram in the upper right that tells us more information about it, about what the link lengths are for this given coupler curve. Now another thing you'll notice is that these coupler curves have dashes on them. And these are for 5 degrees of crank rotation. So sometimes you'll see, like in this case, these dashes are spread out quite widely. Well, this means that I actually have a very high velocity through this area, and then when they are closer spaced, now for each 5 degrees of crank rotation means I'm not moving as far, so I have lower velocity. So we can get even more information from these coupler curves than just what's the shape of it. We can also get velocity information. So let me quickly take us to a synthesis problem, and then we'll open up the atlas and look at some possible curves. Here's the path generation synthesis problem I pose. Let's create a painting mechanism that basically takes a roller and guides it along a wall right here. So this would be the painting period, and then brings it down into a painting tray and dips it, and then perhaps brings it back up, and then we roll it down the wall again. So hypothetical application where we might have this handheld painting mechanism or painting robot. And I want to traverse this path right here over and over again. So a mechanism seems like a good thing to do that. But how do we synthesize it? Now, really the tools that we've learned so far are using precision positions. And using precision positions, I could try to place maybe precision position 1 up here, maybe 2 down here, and maybe 3 over here. And if I could add a 4th maybe to help guide it through the motion. But I really don't know what it's going to do in between. So how can I help myself? Well, there's some approximation methods where I could have more precision positions, but they're approximate. Or perhaps I could go to an optimization method, so I could say this is the path I want to follow, and then I could optimize it as close to that path as possible. Or alternatively, I could flip open this enormous atlas, and from this try to find a coupler curve that is a decent approximation of what I want to create. So let me now open up this coupler curve book, and we can talk about what these actually look like. So my coupler curve book looks like this. So here is one page out of the Rones and Nelson Atlas that I happen to have. And again, I can locate my ground pivots by the 3 circles, the moving pivots by 2 circles. And what I'm going to start to do is basically flip through the pages of this book and find where do I start to get a coupler curve that does approximately what I want it to in terms of a relatively straight line along the wall, and then a relatively straight line that's at a slight angle that dips down into my paint area of the bucket, and then repeats that process over and over again. So what I'm going to do is basically scroll through all of these pages, and I can start to see, wow, I get some variety of things where I get some loops in here. I can perhaps get some other behavior that is quite complex. And you'll notice that these are kind of grouped based on moving through a set of rows of coupler locations. So here my coupler points are actually right on the coupler itself or extended out from it. And then I'll move down to the next row, and now these are below it. And I get kind of sets or groupings of various coupler curves. Here I'm 2 rows below it. And I'd basically take this 700-page book, or the electronic version of it, and I'd scroll through it and try to find myself a good coupler curve. So with that in mind, let me jump back to my PowerPoint slide with one page that I think does a pretty good job of that. All right, so here's a page out of that Rones and Nelson Atlas that I happen to pull out, thinking that this does a pretty good job of approximating the motion that I wanted for this painting mechanism. You might say, well, didn't you want this vertical line relative to where you were dipping into the painting mechanism? Well, let me propose that this is the approximate straight line of the wall, and all I need to do is rotate my mechanism a little bit. So I have this approximate straight line right here, and then another approximate straight line that might be doing the dipping. And maybe this coupler curve doesn't do quite what I want, but notice that its neighbor here also has a relatively straight section, and then a straight section that would be doing the dipping into the painting. And so maybe I could create a mechanism that's somewhere in between these two. So first of all, let's just talk about how to actually take a mechanism out of the Rones and Nelson Atlas and do something with it. So what I need to do is basically recognize this is the first ground pivot of my mechanism, right here. Here is the moving pivot, so this is my input link. My output link actually has a ground pivot and it's slightly off the page, but I get enough information within this table right here to tell me that the length of the output link is 4 in this case, and the length of the ground pivot is, the ground link is 4 as well. So hypothetically, let me just place it right here, even though I know it's slightly off of my page. And then my ground link will connect these, and then my coupler will connect these two moving pivots. Now to get out to this coupler curve I want, I happen to pick the, let's say this second from the right. This would be the coupler curve that I want. And so my coupler would actually extend out to that point, and then to show that it continues, I'm going to add that little mark right there. And then this guy will follow that entire, this entire coupler curve that I had right here as the crank makes an entire revolution. All right, so I've got that information, but maybe I want to visualize this a little bit better. So I'm going to take us to another piece of software, the program Linkages, and we'll talk about how to input this information into linkages. So here I've opened up the program Linkages, and when I first launch it, there's actually a couple of error messages because it was written a very long time ago, but if you just click through those as ignore them, it comes up just fine. Now, when it first comes up, you'll notice that it's in a synthesis mode where I actually have 4 precision positions, and in this little drop-down box here, it says that it's 4 precision position motion, and if I scroll down here, I can get to the sketch mode. Now, in the sketch mode, I can take all of these points, drag them around, and as I do so, you'll notice that my coupler curve changes, and I can also take the coupler point itself, move it around. I can move all sorts of things around and be able to create this and then be able to animate it and watch it move through its entire range of motion. So what I'm going to do is take that information from the coupler curve that I found in the Rones and Nelson Atlas. I know my crank length is 1, my output link I believe was 4, and the distance between my ground pivots was 4. I'm going to take all that information that I had and I'm going to create a sketch from it. So I already did that, and this is what the solution looked like. Now, I could, to give me more information about, how do I actually know these values, I click on this little icon right here that says linkage information, and it pops open this box right here, which tells me this is a crank rocker, and here's where the input link is located, or the ground pivot, which is approximately 0, 0. My output link is about 4 inches, or 4 units, whatever it happens to be in this case, and again 0 on the Y, so I've got about a distance of 4 here, and all of these other values. So I tried to input this as close as I could to what the values were from the Rones and Nelson Atlas. And you can see then I can animate this and watch it move through that range of motion. I can also have it flip directions and go the other way and dip into my paint bucket, come back up, and you'll notice that I need to do probably a little bit more rotation of this ground pivot to get this to be a vertical motion, but I'm quite close here, and this sketch mode allows me to tweak things fairly quickly. In other words, I had said before that I wanted to be somewhere between the first and second coupler curves, so I could make this slightly longer and move towards that other coupler curve where I had a little bit longer flat segment down here. So this allows me to very quickly jump from one coupler curve to the next and be able to say, oh, well, what if I move that just somewhere in between? I can get the coupler curve that I want. So a very fast way to iterate and come up with a path synthesis problem, or a path synthesis solution. So now let's go back and talk about how to use these coupler curves from the Rones and Nelson Atlas for dwell synthesis. So we're now going to look at doing dwell synthesis here, and dwell again is this period of rest, or what we call stasis, of the output link while the input link continuously rotates. So we might do this when we're holding a clamping operation, or for some other reason we want the mechanism to rest while the rest of it is still moving. So there's a couple of ways to synthesize this. One is what we call the arc method. So here what I would do is I'd go to my Rones and Nelson Atlas or some other way of synthesizing a mechanism, and I would find a coupler curve that has an approximate constant radius arc to it. So something like this. Now it'll never be a perfect arc, but the closer it is to a perfect arc, the better our dwelling will be. So there's a 4-bar mechanism that creates this coupler curve. I'm not showing that 4-bar, but again, this comes from the Rones and Nelson Atlas. Now what I do is I basically say, let me find the center of this arc, and so I'm going to set up 3 positions, C1, C2, C3, that go along that arc, and then I use perpendicular bisectors to find this location right here, which is at the center of that arc. So as my coupler point would be moving through those 3 locations, this point right here, if I had a link connected here, it would just rotate about that point, but the other side of this link could just stay stationary. And then to add this to a mechanism that's actually doing this rocking back and forth, now I have to have another ground pivot. So I basically create a 6-bar linkage where I have the initial 4-bar, I add this connecting link, link 5, and then I have this link that is doing the dwelling, link 6. So as the 4-bar goes through its range of motion, I have link 5 moving through this path, and this location between link 5 and link 6, which we call D here, stays stationary as I'm moving from C1 through C3. And then as I move off of this location, now we find the maximum extent that it moves away, which would be C4 right here. And as I connect that over, that would then cause that link to move over to this location. So this is during the non-dwelling part of the mechanism, or the motion would be over here. So this link right here, link 6, is basically oscillating back and forth. And during this period where I'm going from C1 through C3, it stays stationary in the left position, dwelling. Now another option is I can use what we call a straight line method, where I look for a coupler curve that has an approximate straight line like this, or perhaps like this one where I have a straight line and then this crew node that's crossing it. And now I set up a ground pivot that's along the axis of that straight line. So this ground pivot that I'm calling O6 right here, and then I have a link within a slider block on it. So you can imagine that as my 4-bar, which is not shown here again, is moving through this coupler curve, as it moves along this straight line section, I get my slider block just sliding along link 6, but link 6 is actually just sitting stationary or dwelling as that's occurring. The same thing in the right diagram, but then I have a crew node that moves beyond that in either direction. So again, gives us quite a bit of capability, and I can take this even farther and find one of these perhaps symmetric coupler curves, and then use 2 straight line sections to help me dwell in 2 locations and then oscillate between those. Now one problem with these straight line methods is that we have to have a slider now, which does have higher friction and a little bit more problematic than the purely pinned mechanism of the arc method. So I'm going to leave it as an in-class activity to do synthesis of a dwell mechanism, but wanted to really expose you to the idea of an atlas which has thousands and thousands, 7,000 in this case, coupler curves that allow you to very quickly look through and find a decent solution, and then maybe fine-tune it from there, either to do path synthesis or do something like this where we want to do dwell synthesis.